Hi, let's talk about drawing free body diagrams of real objects. In this video, we're going to concentrate on this pair of pliers, a relatively ordinary object doing a relatively ordinary job, and that's pushing on these arms in order to squeeze this screw. In order to examine this, we're going to draw a free body diagram of this object. So I'm going to go ahead and measure the object, draw a quick picture of it, and then solve for the reactions throughout the object based on an applied force here at the arms. So what does this pair of pliers really look like? It's two pieces connected by a simple pin. And so we're going to draw a free body diagram of just this one piece, extending from here, where I'm gripping the object, through this pin, and all the way out the arms to where the force is going to be applied by the user. Let's draw that sketch. I'm going to put this down on the board right here, sketch this thing out, and I'm going to use a little freehand here. And there's the pin right there at the center. Now I'm going to go ahead and get a ruler, just like this one, and I'm going to measure this thing and put some dimensions on my diagram. So I used my tape measure and I got some quick dimensions of our plier arms. You can see it's about 1.5 inches from where I'm going to be grabbing that screw to the pin, and from the pin to where I'm applying the force of my hand, about 4 inches. The precision of these measurements obviously will drive the precision of the final answer. But I've done something when I pulled this one arm off of the other arm and I removed that screw. I need to replace each of those things with what's being done by those objects. So when I push with the pliers on the screw, there's going to be an equal and opposite reaction back from that screw, which we'll call F sub S. And that's going to be acting directly in the Y direction. For the pin, I've got a couple of forces going on, right? When I pull a pin, I know that there's no moment about the pin because the pin does not resist rotation. But I know that there is potentially a force Y and a force X. And I've started using my axis system, so I better put an axis system up here to make sure that anybody taking a look at this knows exactly what they're looking at. And there's my Y direction and my X direction. The last force I need to add is the force that's being applied by the user of the pair of pliers. And that's going to be right here. And we're going to call that Fk for force Klosky. So how hard is Fk? We've got to make some kind of assumptions to move forward with our analysis. And that first assumption is I'm going to assume that Fk is equal to 25 pounds. So that the user is pushing down on that arm with a force of 25 pounds. That might or might not be reasonable, and I might have to actually go and make some measurements to figure out what a reasonable and comfortable force from the user might be. Now that I've got that force from the user, though, I can figure out what this force on the screw is. How would I go about doing that? The answer is I would need to use the basic equations of equilibrium. We have 3 equations of equilibrium available to us in this two-dimensional world, and those are the sum of the forces in the X equal to 0, sum of the forces in the Y equal to 0, and the sum of the moments about some point are equal to 0. Now my sum of the forces in the X, not particularly helpful, is it? How many forces are acting in the X direction on this object? Just this one, right here at the pin. And if that Fx is anything except 0, then my pliers are flying through space like Buck Rogers or something. And that's not what's happening. These pliers are at rest. And so my sum of the forces in X is equal to 0, What does that mean? That means force Fx is equal to 0 there at the pin. The sum of the forces in the y is also equal to 0, but I might not even need to know that. What I'm looking for is the force on this screw right here. And I can use this moment equation cleverly so that I never have to solve Fy. If I want to know Fy later, I can figure it out. But I asked what is the force applied on that screw. And to get after that, we're going to take the sum of the moments about this pin. So we'll take the moments about the pin equal to 0. And that's equal to, and we'll start at the left and we'll work to the right. And I'm going to say that the moments going counterclockwise are positive. So as I move from the left to the right, I first encounter the force Fs, and I maybe should zoom out a little bit here so you can see this better. There we go. That force F sub s, and which way is it acting? About that pin, we're going to use that right-hand rule, and Fs is tending to spin the object counterclockwise, so that's a positive moment. So the force, F sub s, times the moment arm, 1.5 inches, is going to be the moment caused by the screw. Now, what's the moment caused by force Klosky? It's actually acting in the negative direction. And it's going to be negative Fk. Take a second and think about what the moment arm is. Okay, it's that 4 inches. How far from the line of action of Fk? There's that line of action. There's the pin. And the line of action, Fk, to the pin is 4 inches. And so if that line of action is 4 inches, then we can do a little bit of algebraic manipulation on this same equation. And it's F sub s is equal to Fk times 4 inches divided by 1.5 inches. Now, how many times does 1.5 go into 4? It goes in 2 2/3 times. So that means that F sub s is equal to 2.667 times Fk. And wow, now we've got the power of a pair of pliers. Why did we even make this thing? We made this object because the force applied to the screw is 2 2/3 times as large as the force that I'm going to apply. So I can squeeze that screw with a 25-pound force. With a 25-pound force, I'm applying something like 2.66 times 25. Probably should have had this in my back pocket when I got out here. It's not quite 75. It's going to be about 70, something like that. Hold on, I'm going to pause the video and figure it out. Engineer without their calculator isn't much. So let's fire this thing up, and I'm going to get 25 times 2.667, and I'll get a final answer of about 66.7 pounds. Double underline ANS. And so we can see the power of drawing free body diagrams of real objects in order to figure out the answers to important questions like how hard can I squeeze a screw with a pair of pliers.